Welcome back to our heat transfer class, where we are delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of InnoEnergy. Remember that the introduction to heat transfer is divided into several lessons. In the fourth lesson, you can find a description of the physical phenomenon that allow thermal energy to be transferred when there is a difference of temperatures. Heat transfer mechanisms, which are conduction, convection, and radiation. In the following lessons, we are going to answer the burning question raised in our first video: how fast is energy transferred when there is a temperature difference, within a system or between systems? In this fifth lesson, we're about to discover the secrets of how fast heat is transferred when temperature differences within solids come into play. Therefore, we will start studying the rate equation for the mechanism of conduction. The rate equation for conduction was postulated by Jean-Baptiste Fourier.
Fourier's law is phenomenological, that is, developed from observed phenomena rather than being derived from first principles. Hence, the rate equation by conduction is a generalization based on experimental evidence. Let us go to the lab to do some experiments. We are going to use a cylinder of constant section and perfectly insulated in its lateral surface to avoid energy losses. It is inside this thermal conductivity meter. Its diameter is d, its cross-sectional area is A, and its length is L. We put the left face at a temperature T1 and the right face at a temperature T2, lower than T1. We measure the heat flux, Q divided by A, in watts per square meter. The heat transfer rate is calculated from the cross area and the heat flux. We do some experiments changing the geometry, in example diameter and length, as well as temperatures and materials. Let's go back to class to analyze the results. We have started in the lab using a homogeneous stainless steel cylinder, with a diameter of 50 mm and a length of 150 mm. The temperatures are 323 Kelvin and 298 Kelvin, respectively. The measured heat flux is 2,833 watts per square meter, and the heat transfer rate around 5.56 watts. The first thing we did is to take a cylinder of the same material, the same length but with a larger diameter, d, in this case 60 mm. We see that the heat flux remains the same, but the heat transfer rate increases to around 8 watts. Therefore, we deduce that the heat transfer rate is proportional to the cross-section of the cylinder. The second experiment was to take a cylinder with the same material, with the diameter of the base case, but with a length of 100 mm, shorter than the one of the base case. The result is that both the heat flux and the heat transfer rate increased. Therefore, the heat flux is inversely proportional to the distance between the two faces of the cylinder. Keeping the base case geometry in material, we have changed the boundary conditions by increasing T1 to 400 Kelvin. We see that both the heat flux and the heat transfer rate increase. Therefore, the heat flux is directly proportional to the difference in temperatures. The last experiment consisted in replacing the cylinder of stainless steel by one of aluminium with the same dimensions and boundary conditions. We observe that aluminium has a higher heat transfer rate and also a higher heat flux. Stop the video here and, using all these experimental observations, formulate a rate equation for conduction. Focus in the heat flux equation first. Have you made a proposal for the relationship between the heat flux, the temperature difference and the cylinder length? Let's answer this question together. The first thing to do for evaluating the heat conduction inside a solid is to define a coordinate system. We will call x the coordinate corresponding to the axis of the cylinder. We have observed that the heat flux is directly proportional to the temperature difference between its two faces and that it is inversely proportional to the length of the cylinder. In this coordinate system, the length of the cylinder is equal to delta x, the spatial displacement or distance. We have seen that this proportionality depends on the material. We call thermal conductivity to the proportionality parameter. Substituting the differences of T and X by derivatives, the result is that the heat flux is directly proportional to the derivative of the temperature with respect to X. The minus sign indicates that the heat flux is positive in the direction of X when the derivative is negative, that is when the temperature decreases with X. This is the Fourier's law in one dimension of space. It is in fact the X component of the heat flux. In a three-dimensions analysis, we must take into account the heat flux in the directions of y and z, respectively. Let us consider the unit vectors in each of the directions of space. In 3 dimensions, heat flux is a vector with 3 components. Each component depends on the thermal conductivity and the partial derivative of T in this direction. This is the Fourier's law in 3 dimensions. For isotropic materials, the thermal conductivity is the same in all directions. For isotropic materials and using the nabla operator, we can postulate Fourier's law in a compact expression. After Fourier's law, we can see that the heat flux is normal to the isothermal surfaces. We have seen that the heat flux depends on the material. We call thermal conductivity to the parameter of proportionality between the heat flux and the temperature gradient. For isotropic and homogeneous materials, lambda does not depend on the position or direction, respectively. With respect to temperature, as shown in the figure, thermal conductivity changes with temperature for all materials. In our models in which we will consider the thermal conductivity to be constant, we will take an average value in a range of temperatures limited by the boundary conditions of the problem. We will start by studying one-dimensional conduction. It is characterized by the variation of the temperature being 0 in 2 of the directions of space. This is the case of the cylinder that we have used for the deduction of Fourier's law. Since it is laterally insulated, there is only temperature variation in the x direction. In this case, the isothermal surfaces are parallel disks, as shown in the figure. The heat flux will still be a vector, but with only one component. Please notice that for applying Fourier's law, it is needed to know the temperature derivative. Don't miss the video about the heat diffusion equation. The solution of the heat diffusion equation will provide the value of the temperature at any point and at any time.